Hello, I have been working on this diagram and I am about ready to try applying a scaling transformation to this thing. Not this one. After the fold out, I'm going to apply a scaling transformation. And so I'll do the fold out by changing this show fold out to true, and it will show the fold out. There are a few errors here which seem like they might be of a concern. Complex infinity encountered. I don't know exactly where that happened, but there's probably a couple of dots missing somewhere in this diagram. But anyway, what I'm going to do first, I want to apply another transformation to the dots right after that fold out, which will basically apply a transformation of, well, let's say I have the coordinate x comma t. What am I going to do to that? I'm going to map it to, I'm going to shrink the x-coordinate by a factor of t. And I'm going to leave the t variable alone. Now this is what George Dishman calls Milne's model. He's wrong. This is not Milne's model. Now Paul Gradenwitz has another transformation in time, or transformation in mind, where I take x comma t to a mapping that makes the x whatever changes x to x final comma t, and x final is the width of the space. Actually, maybe that is x over t, because remember t is a number smaller than 1 here. So actually this x divided by t is going to make the x spread out towards the bottom. Anyway, I'll give this a shot, and I'm going to call this show scaling, and basically I'm going to say if show scaling comma, well, it's going to be the same form as this one, except that instead of fold out, we're going to use scaling. And I have not created that function yet, so I will have to do that. It's going to be very similar to the fold out function. It'll be called scaling x underscore comma t underscore. And do we need a module? I don't know if it's going to be that complex. No, it's just going to be x over t comma t. I think that's all it's going to be. But we have this problem that an infinite expression is occurring all the time. Why? Because we have, well, I'll just set t, if t equals 0, we'll set it to 0 comma 0. Otherwise, x of t comma t. I suppose we could even just use x comma 0 and see what happens, because I'm pretty sure everywhere in our code that x equals 0, we also have t equals 0. So let's see how that works. Ooh, it makes an amoeba. Wow, that's cool. Okay, so you can see here that that I was right, that although obviously I had not been right for very long because I just realized this at the beginning of this video, but the 1 over t function that basically the 1 over t function applied to this gives straight co-moving lines for all of the observers. Of course, it doesn't when you come back down to the origin, because the origin is a point, an event, is a single point, and so it doesn't work at that point to divide anything by 0. but yeah, now using those Euclidean coordinates in this mapping, you have the Euclidean coordinates uh, simultaneity plane going down like this and like this. And if I this is not Milne's model, definitely. Milne's model is the one. I mean, you just don't do these you just don't do these mappings in Milne's model. Um, but this does appear to be what would happen to the Euclidean coordinates if you made the if you did the swing down and then did a scaling. All right, well that was very quick. Thanks for watching.